Before I get into this, I need to correct the framing in that title because I don't want to leave you with the wrong impression. Voyager 1 didn't pick up a message, a transmission, or anything resembling a signal from an unknown sender. What it actually detected is something considerably stranger once you understand it properly. A persistent, continuous hum coming from the plasma, filling the space behind it, in the direction of interstellar space the spacecraft is now moving through. NASA does understand broadly what's causing that hum. What NASA genuinely cannot yet explain, and has said so publicly, is the specific physical mechanism actually producing it. Two competing explanations that would mean fundamentally different things about the nature of the space between stars. And researchers currently have no way to determine which one is correct. This is the real story of the sound Voyager 1 has been picking up from behind it since 2017, why it took a young researcher's careful reanalysis of old data to even notice it was there, and exactly what part of this mystery genuinely remains unsolved. If you want accurate space reporting instead of manufactured mystery, subscribe now, because this specific question is still open. Let's start with where Voyager 1 actually is, because behind it, in this headline, refers to something very specific, not some vague, undefined direction in space. On August 25th, 2012, after a journey lasting 35 years, Voyager 1 crossed the heliopause, the outer boundary of the massive protective bubble our sun inflates around the entire solar system, called the heliosphere. That crossing made Voyager 1 the first human-made object in history to leave the direct influence of our sun and enter true interstellar space, the vast region between star systems, filled with an extremely thin, sparse collection of ionized gas called plasma, left behind by the deaths of massive stars scattered throughout our galactic neighborhood over millions of years. Every instrument aboard every previous spacecraft in history had only ever measured conditions from inside that solar bubble. Voyager 1 became the first to actually sample what exists on the other side, and it's been drifting deeper into that same interstellar plasma, moving away from the sun ever since. That's the behind it this headline is actually referring to, not some unknown direction hiding a mysterious source, but the specific region of interstellar plasma stretching out behind Voyager 1 as it continues its permanent journey away from our solar system. And starting in 2017, something in that plasma began showing up in Voyager 1's own instrument readings that nobody had specifically identified before. If a story built on real, verified NASA and JPL reporting instead of manufactured mystery is the kind of thing you want more of, drop a like on this video right now. It genuinely helps this content reach more people who'd get value out of it. Here's how that discovery actually happened, because it wasn't the result of Voyager 1 suddenly detecting something new. It was the result of a researcher going back through data the spacecraft had already been collecting for years and noticing a pattern nobody had properly identified. Stella Ocker, working with Voyager 1's plasma wave subsystem data, an instrument that essentially listens for oscillations in the surrounding plasma using two long antennas extending out behind the spacecraft, had access to a record that, up until that point, mostly consisted of rare, dramatic bursts of activity. Roughly once a year, a powerful eruption from our own sun would ripple all the way out to interstellar space, striking the plasma surrounding Voyager 1 and producing a brief, unmistakable spike that the instrument would clearly register, giving scientists only an occasional scattered snapshot of the plasma density surrounding the spacecraft, separated by long stretches of what looked like empty, uneventful data. Looking more carefully at exactly what sat in those supposedly empty stretches between the dramatic annual bursts, Ocker found something that had actually been there the entire time, simply too faint and too easy to dismiss as background noise for anyone to have properly flagged it before. A weak, but genuinely persistent signal present almost continuously rather than showing up only during rare, dramatic solar events. NASA's own description of the discovery captured the shift in perspective this represented, comparing Voyager 1 to a life raft dropped from a much larger ship, our own solar system's heliosphere, now surveying the actual, ongoing currents of the wider ocean surrounding it, rather than simply reacting to the occasional storm. If you found this discovery process as interesting as I did while researching it, drop a comment and let me know. It genuinely helps me figure out what to cover next. This is where the science becomes genuinely important to understand precisely, because what Voyager 1 is picking up is not, in any sense, a transmission or a communication. It's the natural oscillation of the extremely sparse plasma-filling interstellar space, essentially the physical vibration of that ionized gas itself, detected by Voyager 1's own antennas the same basic way you might notice the ambient resonant hum of a very large, mostly empty room. As Voyager 1 continues moving deeper into interstellar space, the specific tone or frequency of that persistent emission rises and falls, and researchers realized that pattern was directly tracking the density of the surrounding plasma. Denser plasma, producing a higher frequency oscillation. Sparser plasma, a lower one, a relationship rooted in basic, well-established physics. For the first time in human history, that gave scientists something genuinely new. a running, nearly continuous measurement of conditions in interstellar space itself, rather than a scattered handful of snapshots gathered whenever a solar storm happened to reach far enough to register. It helps to understand a bit about the actual hardware responsible for this entire discovery, because the plasma wave subsystem is a genuinely elegant piece of 1970s engineering that's still doing exactly what it was originally built to do, nearly 5 decades later. The instrument relies on 2 long antennas, each extending about 10 meters, roughly 30 feet, out behind the spacecraft in a V-shaped configuration engineers have informally nicknamed the bunny ears. As the extremely sparse plasma surrounding Voyager 1 oscillates, those antennas pick up the resulting electric field fluctuations directly, and the specific frequency of that oscillation corresponds mathematically to the density of the surrounding plasma. The instrument doesn't need to physically sample or touch the plasma at all. It simply needs to listen to how the surrounding charged particles are naturally vibrating, translating that vibration into a genuine, quantifiable density measurement, then transmitting that data back across billions of miles to Earth using hardware that predates the personal computer. Now, here's the part of the story where the NASA can't explain it framing actually becomes accurate rather than exaggerated, because there's a real, specific, unresolved scientific question sitting at the heart of this discovery. The persistent emission Voyager 1 keeps detecting has 2 genuinely different possible physical explanations, and researchers working directly with this data have been explicit that they have not yet been able to determine which one is correct. The first possibility is that the emission represents what scientists call thermally excited plasma oscillations, essentially the natural, spontaneous vibration of plasma particles interacting with each other and their surroundings simply due to their own thermal energy. If that explanation turns out to be correct, it would represent a genuinely significant discovery in its own right, but one that would fit comfortably inside existing physical frameworks describing how plasma behaves, without requiring scientists to fundamentally rebuild any of their underlying models of interstellar space. The second possibility is that Voyager 1 is actually detecting something called quasi-thermal noise, a related but physically distinct phenomenon that also carries information about plasma density and temperature, but through a subtly different underlying mechanism than straightforward thermal oscillation. If this second explanation turns out to be the correct one, it would require existing models of the interstellar medium to be substantially revised, because it would mean the plasma surrounding Voyager 1 is behaving in ways current theory doesn't fully account for. If you found this specific unresolved question as genuinely intriguing as I did, drop a comment and let me know. It genuinely helps me figure out what to cover next. Distinguishing between these 2 possibilities isn't simply a matter of researchers needing to think harder about data they already have. It genuinely requires either additional data gathered directly by Voyager 1's own instruments, which are producing less usable data every single year as the spacecraft's shrinking power supply forces engineers to shut down more of its remaining systems, or an entirely new mission specifically designed and built to study interstellar space, using instruments capable of making the more detailed, more precise measurements needed to definitively settle the question one way or the other. As of right now, no such mission exists, none is currently funded. And based on realistic estimates of how long it would take to design, build, launch, and fly a spacecraft all the way out to the heliopause, even if funding were approved today, the next spacecraft capable of directly sampling interstellar space and testing this exact question wouldn't arrive at that boundary for at least another 25 years. That timeline matters enormously for understanding why this specific mystery genuinely qualifies as something NASA can't currently explain, rather than something that's simply awaiting a straightforward, already planned follow-up study. When Voyager 1 eventually goes silent, whenever its shrinking power supply finally drops below the minimum threshold needed to keep any remaining instrument running, the specific question of whether this persistent plasma hum represents ordinary thermal oscillation or the more theoretically significant quasi-thermal noise will very likely remain genuinely unanswered for decades afterward, with no other instrument anywhere near interstellar space capable of continuing the investigation. It's worth understanding that Voyager 1 isn't actually the only spacecraft contributing to this specific investigation either, because its twin, Voyager 2, crossed its own heliopause in November of 2018, roughly 6 years after Voyager 1, approaching from an entirely different direction. Voyager 2 carries its own plasma wave subsystem, and researchers have compared data from both spacecraft to check whether the same kind of persistent plasma activity Voyager 1 detected shows up consistently on the opposite side of the heliosphere as well. That comparison matters directly for the specific mystery covered throughout this video, because if both spacecraft, sampling entirely different regions of interstellar space in entirely different directions, show broadly similar plasma behavior, that consistency helps rule out the possibility that Voyager 1's detection reflects some kind of unusual, localized fluke specific to the exact patch of space it happens to be passing through, rather than a genuine, broader property of the interstellar medium surrounding our entire solar system. Confirming that consistency across two independent spacecraft, approaching from different directions, is exactly the kind of cross-checking that gives researchers real confidence the persistent emission represents something scientifically meaningful, even while the specific underlying mechanism, thermal oscillation or quasi-thermal noise, remains unresolved on either spacecraft's data individually. It's worth understanding what's actually at stake scientifically in finally resolving this question, because it isn't merely an academic technicality. For decades before Voyager 1 ever reached interstellar space, scientists built detailed, carefully tested mathematical models describing what conditions in that environment should look like, generally predicting a relatively quiet, smooth, sparse plasma environment where particles drift slowly and comparatively little happens compared to the more energetic, turbulent conditions found inside our own solar system's heliosphere. What Voyager 1 has actually found, regardless of which of the two specific explanations for this particular emission eventually turns out to be correct, already paints a considerably more active, more structured picture of interstellar space than those earlier models predicted. Researchers studying the data published in the journal Nature Astronomy have described interstellar space as genuinely turbulent, with real structure existing across scales ranging from mere meters up to distances measured in millions of miles, a level of complexity that was essentially invisible to scientists before a physical instrument was actually sitting out there to measure it directly. If the persistent emission ultimately turns out to represent quasi-thermal noise rather than simple thermal oscillation, that finding would add yet another genuinely significant layer to that already revised picture, suggesting the plasma surrounding our solar system behaves in ways that existing theoretical frameworks, built before anyone had direct measurements to test them against, simply didn't anticipate. That's precisely the kind of open question serious astrophysicists take seriously, specifically because resolving it either way would matter. Not because the mystery itself has been dramatized beyond what the actual science supports. There's something worth appreciating about how this entire mystery actually surfaced in the first place, because it reflects a genuinely important, if unglamorous, part of how real scientific discovery actually works. Nobody built a new instrument specifically to find this persistent plasma hum. Nobody launched a dedicated mission to go looking for it. It was sitting quietly in data. Voyager 1 had already been transmitting back to Earth for years, embedded in the supposedly uneventful gaps between the rare, dramatic solar bursts that had originally captured researchers' attention. It took a specific, deliberate decision by Stella Ocker to go back and look more carefully at exactly those overlooked stretches of data, treating what everyone else had assumed was empty background noise as something potentially worth investigating on its own terms. That's a genuinely common pattern in real scientific breakthroughs. Discoveries hiding in plain sight within data that's already been collected, waiting for someone willing to look at it from a slightly different angle than everyone before them had. It's also worth being clear about why this specific mystery hasn't simply been resolved through more careful analysis of the data Voyager 1 has already sent back, because that's precisely the kind of clarification a headline like this one tends to skip over entirely. Distinguishing between thermally excited plasma oscillations and quasi-thermal noise isn't a matter of researchers needing more time to crunch existing numbers. The two phenomena can produce genuinely similar-looking signals within the specific frequency range. Voyager 1's plasma wave subsystem is actually capable of measuring, meaning the instrument itself, remarkable as it's proven to be for an object launched in 1977, simply wasn't designed with the kind of additional measurement precision that would be needed to cleanly separate the two possibilities from each other. That's a genuine hardware limitation, not a gap in analytical effort, and it's exactly why researchers have been so clear that resolving this question really does require either a fundamentally different kind of instrument or additional corroborating data that Voyager 1's current, aging hardware simply isn't built to provide on its own. It's also worth connecting this specific unresolved question back to why the heliosphere matters for reasons considerably closer to home than pure academic curiosity. The heliosphere isn't simply an interesting boundary marking the edge of our solar system. It functions as a genuine physical shield, deflecting a meaningful portion of the high-energy cosmic radiation streaming in from distant, long-exploded stars elsewhere in the galaxy, radiation that would otherwise reach the inner solar system, including Earth, at considerably higher intensity than it currently does. Understanding precisely how the plasma pressing against that shield from the outside actually behaves, whether its persistent oscillations reflect ordinary thermal activity, or the more theoretically significant quasi-thermal noise, feeds directly into how accurately scientists can model that shield's own long-term behavior and effectiveness, an issue with genuine, if indirect, relevance to conditions here at home, even though nobody is suggesting any kind of imminent danger tied to this specific open question. Now, bringing this story fully up to date matters too, because the spacecraft responsible for this entire discovery is genuinely running out of time, and that adds real urgency to an already difficult scientific question. Voyager 1 runs on power generated by 3 radioisotope thermoelectric generators, converting heat from the natural radioactive decay of plutonium-238 into usable electricity. And that power supply has been shrinking by roughly 4 watts every single year since launch, with absolutely no way to replenish it. In late February of 2026, during a routine maneuver, engineers detected an unexpected drop in the spacecraft's available power, bringing Voyager 1 dangerously close to triggering an automatic safety mechanism called undervoltage fault protection, a self-preservation system that would have forced a shutdown of critical spacecraft functions and required a risky, multi-day recovery process conducted, like every command sent to this spacecraft, across a communication delay now stretching past 23 hours each way. To stay safely ahead of that threshold, engineers at NASA's Jet Propulsion Laboratory made the difficult decision to manually retire one of Voyager 1's remaining working instruments before the situation could force their hand entirely. On April 17, 2026, the team sent commands shutting down the low-energy charged particles experiment, an instrument that had been operating almost continuously since the spacecraft's 1977 launch, providing nearly 49 consecutive years of data. Kareem Badruddin, Voyager's mission manager at JPL, was direct about how the team viewed that decision, stating plainly that shutting down a working science instrument was nobody's preference, but that it remained the best option available to keep the spacecraft itself functioning for as long as possible. That leaves Voyager 1 with exactly 2 functioning science instruments as of right now, a magnetometer measuring the magnetic fields of the interstellar medium, and critically for this specific story, the plasma wave subsystem responsible for detecting the persistent emission covered throughout this video, still quietly listening to the plasma surrounding the spacecraft. Engineers have been testing an experimental power management procedure nicknamed the Big Bang, first attempted on Voyager 1's twin, Voyager 2, during May and June of this year, specifically to determine whether reconfiguring how the spacecraft's remaining power gets distributed could free up enough additional electricity to keep both remaining instruments, including the one responsible for this exact mystery, running for meaningfully longer. If that procedure succeeds and gets successfully applied to Voyager 1 as well, it could extend the window during which scientists have any chance at all of gathering the additional data that might eventually help distinguish between thermal oscillation and quasi-thermal noise, the 2 competing explanations still sitting entirely unresolved. There's a broader point worth sitting with as this story wraps up, one that extends past this single unresolved question about plasma physics. Voyager 1 was designed with an expected operational lifespan of roughly 5 years, built to complete flybys of Jupiter and Saturn before its mission was considered complete. Everything covered in this video, the interstellar plasma measurements, the persistent hum, the genuine, still unresolved scientific question at the center of it all comes from work. The spacecraft was never actually designed or expected to perform in the first place. That's precisely why the decisions NASA's engineering team has had to make this year, shutting down working instruments to conserve dwindling power, testing an experimental and previously unattempted power reconfiguration procedure, carry so much weight. Every additional month this specific instrument keeps functioning represents additional data toward a genuine, unresolved scientific question that no other spacecraft anywhere in the solar system is currently positioned to investigate. And once it finally goes silent, that particular line of direct, real-time inquiry closes, potentially for a generation or more. So what does all of this actually add up to? Voyager 1 hasn't picked up any kind of message or transmission from an unknown source, and describing this discovery that way would be a genuine misunderstanding of the underlying science. What it has done, consistently since 2017, is detect a real, physical, nearly continuous oscillation in the plasma filling interstellar space behind it. First identified through Stella Ocker's careful reanalysis of data that had been quietly sitting there, unrecognized, for years. And there genuinely is something NASA cannot yet explain about this specific discovery. Not whether the emission is real, and not some vague, undefined mystery, but the precise physical mechanism actually producing it. Thermally excited oscillation or quasi-thermal noise. 2 possibilities that would carry meaningfully different implications for how scientists understand the space between stars, with no way to currently determine which one is correct, and no funded, currently planned mission capable of gathering the additional data required to settle the question for at least another 25 years. If stories like this, the accurate version rather than manufactured mystery, are what you come here for, subscribe to this channel and turn on notifications, because Voyager 1's own answer to this exact question may or may not ever arrive, before its power finally runs out for good. Thanks for watching, and I'll see you in the next one.